Okay, we're into 5-3. Yeah, circular functions. 5-3, circular functions. We're starting to work with trig functions now. Sine, cosine, tangent. So this is just the start of the fun stuff to come. I enjoy this stuff. Circular functions. All right, to learn more about sine, cosine, and how these functions work, I'm going to show you something on a graph here of what this does. I'll zoom in a little bit here so we can see. It is, and that's actually where the sound wave comes from. Let's make it just a touch smaller. Okay. If you take a look now, what they're actually, I can put this in radians. How do I want to put this in radians? How do we do that? I don't think, no, that's just putting in a function. Stuff on top, stats. No, miscellaneous. I'm not seeing it right off the top of my head. No. All right. No matter. I want you, plus this open a little bit more. I want it somewhere in between that. Oh well. Here's what I want you to notice. On a sine function, sine stays between 1 and -1. All right? It, with just a sine of x, it'll stay between 1 and -1. How the hills and valleys of the sine go, at this point here, at its vertex right here, is at 90 degrees or pi over 2. All right? Where it touches back onto the x-axis again, right here, 180 degrees or pi. And at this vertex right here, it's at 270 degrees or 3 pi over 2. And where it comes back and touches here, 360 degrees or 2 pi. All right, so that is just a sine. We're just looking at the sine of x here. It stays between -1 and 1, and this is how the waves will come out. It's going to be important to know as you start moving forward and working with sine and cosine, you're going to see that the sine of 90 degrees is 1. The sine of 180 degrees is 0. The sine of 270 degrees is -1. And the sine of 360 is back to 0 again. Okay? If we were to do the cosine now, notice that again, it stays between 1 and -1. But now, when the cosine is 0, it's at 1. At 90, it's at 0. At 180, -1. At 270, 0. And back up to 2 pi 1. All right? If you take a look at this, it's shifting off. It's a shift of 90 degrees between the cosine and the sine. All right? Tangent is a lot different. We're not even going to get in. Tangent's lines that come down this way. Wow. Function. Tangent, I know. There's your tangent. Tangent comes down this way. With tangent, it never will hit at 90 degrees or 270 or 5, or at 180 from that, what's that? 450? It'll never hit at those. It gets really close, but it never quite gets there. All right. The ones that I want to really focus on right now are these. And the reason why this becomes important, if you start taking a look at, I don't need this anymore. If you start taking a look at a circle around a, all right, we'll get there. Eventually we'll get there. It's almost there. Oh, there it is. All right. If you take a look at the quadrants, all right, and if we make this circle around, you'll notice that, bless you, all right, your x here is really at a 1. This is where x equals 1. This is where y equals 1 and x equals 0. Y equals 0 here. So if we started plotting these coordinates, it would look like 1, 0. Up here would be 0, 1. Back here would be negative 1, 0. Here would be negative 0, 0, negative 1. Notice the similarity in what the sine graphs and cosine graphs start doing. This really looks like what? A sine graph, doesn't it? All right, in what you're doing in your numbers. It is. Here's 0. It goes like this. All right. At 0, when sine I'm getting goofed up here. At pi over 2, all right, we've got a value of 1. Y equals sine of x. When x equals 1, I'm off. X equals 0. Yeah, when x equals 0, right here, we are at a y of 1. We're up here. When x equals 1, out this way, we're at 0. All right. This mimics the sine graph and what you're doing. All right. So let's take a look. I wanted this portion of it is not something that is kind of like extra information to help you start understanding the sine and cosine graphs. All right. And this is where it comes in. We're getting back to, remember I told you a good mathematician can derive? They take something and they derive it. Okay, tell me what this looks like. R equals the square root of x squared plus y squared. Okay, so if I'm looking at this and I go into my quadrant here and I put a line coming up here and I drop a line coming down here, make it a right angle, and I call this my x, this is my y, and this is r. All right, this would be like a radius if this is a circle. All right. This is what we're going to start getting into. The similarity of the Pythagorean theorem is where they get this from. So we can derive what we're doing. Now, this gets back into what I started showing you guys last year. And you're going to see a lot of this. If this is 3, if my x equals 3, and my y equals 4, what's r? 5. 3, 4, 5. All right, they'll do a lot of this. If this is 5 and this is 12, what's this? 13. You'll start seeing a lot of this. But it's essentially the Pythagorean theorem, all right, just done with an r, an x, and a y. Based on this. That's what you guys are going to end up working with. So, if we were to take a look at, I'm going to redraw this over here. All this x, my y, and my r. If I'm going to take a look at the sine of theta, and I'm going to call this theta in here. If I'm going to look at the sine of theta, and I remember that my sine of theta equals my opposite over my hypotenuse, we can rewrite this as y over r. Same thing with cosine of theta. Is adjacent over hypotenuse, which equals, in this case, x over r. And tangent theta equals my opposite over my adjacent, which equals y over x. My pocket is just buzzing away right now. They're going on about my mom. I'm on a group text thing, and they are going nuts. It's going bzzzt, bzzzt, bzzzt. A little while later, I can just imagine what's being said. Anyway, this is what we need to work on. This is what we're going to do today. This is the stuff right here that's going to be important, okay? And it's based off of knowing this right here. Okay? Of course. You want to do that instead?